So welcome to this lecture on VHDL in the course Digital System Design with PLDs and FPGAs. In the last lecture we were looking at some examples of given a circuit how to write the code, and given a VHDL code how to infer what is the circuit which could be synthesized from that code and so on, and we couldn't complete that. So I am planning to complete it and get to the digital system design for few lectures before maybe we come back to the VHDL a little bit, again go to some other topics. Okay. So let us have a look at what we have done last lecture. So last lecture we have looked at the ripple adder. So in the ripple adder it's simple, you have a full adder cascaded, and the problem is a delay, and we said for carry look ahead adder basically it's like writing the truth table and implementing it, or working out from the full adder. It means that you have this two equation, one is for sum, one is for carry. The trouble with the ripple adder is that the say Ci plus 1 is kind of derived from Ai, Bi and Ci. Ci is coming out of the previous stage, so it ripples, it adds to the delay. So what the carry look ahead adder does is that you take this and substitute here from the starting with the C0, like C1 is A0 B0 or A0 or B0 and C0, and when it comes to C2 it is A1 B1 and so on. So C1, whatever is the C1 equation is substituted, expanded at a 2 level kind of structure. Only difference is that this is made common, Ai, Bi and Ai or Bi, because that is used everywhere. So that is made common. So there is another kind of level of gates, that's all what it happens. So you get as the substitution goes it gets expanded, one product term becomes extra because of this process, and you have you can see that this is G0 P0 add to a level of gates. So you have 3 levels of gates for the carry, and then the XOR followed with the XOR. So you have around kind of 5 gates delay for all the stages, that is what is achieved by the carry look ahead adder. And we have implemented the sum and Gi Pi in a loop, and the carry equations are explicitly written. Not a big deal, because even if it is to write a 32 bit, it's not a big problem, you can write it. And ultimately at least in the case of plus, most of the time we use the plus operator. It depends how it is implemented, and mostly it will be ripple adder. In FPGA it will result in a built-in adder resource, which we will look at it later when we come to the FPGA part. And we have looked at as an example the shift register, and most of you would have learned somehow you would have coupled this shift with the register, but you should know that there is a register, then there is a shift operation, and when you want to shift by kind of say 1 bit, then it's a matter of wiring, say D6 go to D7, D0 go to D1, this is D1 D-1, and you append a 0. So it's just a wiring, and destination could be a different register. In most practical applications it will be a different register, only very less cases where the destination is same as the source, because you have a data path where the data kind of goes through a pipeline. So there is no way you can push it back many a time, so it goes all the way, unless the algorithm itself has an iteration back, then you iterate over the data path. The example will be some kind of encryption schemes where you do it, iterate it over, which can be unfolded, but then that's a very costly kind of operation, so it is iterated over back through the data path. And but when you need some kind of variable shift, say you want a shift register with shift left, shift right, or you shift by 1 bit, shift by 2 bit, then you need to have a configurable shift that is achieved by a mux. So here I am showing a shift left. In that case the Q6 will get the Q5 for shift left, and if it is shift right then Q6 will get Q5, and if it is a parallel load it will be coming coming from the external input and so on. And there is a select line depending on the number of paths, and this is replicated. So you have an 8 bit register, then you have 8 muxes, and so I said you can view it as 8 separate mux or a huge mux, it depends how you view it, and the coding also can be different depending on that. So the variable shift is done through a multiplexer, and we have seen a universal shift register where you have shift left, shift right and a parallel load, and that is the code. And we have seen we have written a case within the clock event, clock is equal to 1. This one shows separate muxes as a loop, and the second code shows a kind of single muxing. Essentially it is same, but like I am talking in terms of the hardware now, but in terms of the syntax in the VHDL this is kind of loop, and this is kind of what to say, a vector assignment. Otherwise the circuit wise there is no difference. There could be difference because it all depends how the synthesis tool kind of infer the structure and how it is mapped to the underlying hardware and all that. There could be difference for us to try it out. Maybe when we play with the tool we can take some example and have a look at how the synthesis tool handle the various type of coding and so on. So we have seen another example given a block diagram how to code. As I said we can code a register with the preceding logic using a single process, and here it looks like there is some logic preceding it and some logic following it, but this being a kind of cyclic, this can come over here, that is what we have done. And then you can write a process like clock and reset is there. If reset is 1 then Z is 0, otherwise upon the clock if lock is 1 then it is Q plus A, else it is B. So that is what is shown here. If reset is 1 Q is other 0, upon the clock if LOC is 1 then Q gets Q plus A, else Q gets B. It is very simple to write the code, and this is another example. We have got the VHDL code and we kind of worked back to find what is the circuit which is implemented by this, and from this we could, like, you have an A is equal to 1 then the output is 0, otherwise upon the B. So A is a reset, B is a clock. So this is a comparison. Y is compared, the output is compared with some input, and if it is 1 then the data is shifted, the output is shifted version of the present output. The next output is a shifted version of the present, and that is it, otherwise it will hold the value. So you get A as reset, B as a clock, then the Y is compared with C. If it is 1 then a shifted version of the Y along with the D goes in here, otherwise it is kind of recirculated. That is hardware you get, and this is where we have kind of stopped. Okay, this is another code, a VHDL code. Our aim is to kind of find at least draw the block diagram of the circuit and infer what is the function of the circuit. Okay, so at the entity level it is very simple. You have two inputs which are 4 bit U and V, and a single output which is 8 bit. Okay, and there is no clock or reset, so you are sure, at least I have not shown the code, but this being a practical code there is no mention of something kind of sounding like clock and reset. So this is a combination circuit which takes 2 4-bit values and give an 8-bit value. Now coming to the architecture, before the begin we have some declaration a D type 1, it is a new data type which is an array of 4 locations. Each location is 4 bit and we are declaring a Y of this type. Okay. Now that means there is a Y3, Y2, Y1, Y0, each of which is 4 bit. Okay. Now another data type which is again 4 location 8 bit, and we have declared X as that type. That means you have X3, X2, X1, X0, and we have each of X3, X2, X1, X0 is 8 bit, and we have defined a constant that for easy kind of coding, maybe for kind of some symmetry we will see in the code, which is temp, which is a 4 bit vector which is all zeros. Okay, so 4 zeros. Okay, so we will see the code. So remember this, U and V are the inputs 4 bit, W is output 8 bit, we have some intermediate signal Y which is 4 location 4 Ys, Y3, Y2, Y1, Y0, each of 4 bit, X3, X2, X1, X0 each of 8 bit. Okay, now let us go to the code. So look at this, there is a generate loop now. As I said, U and V are the input and Y is a 4 kind of values, 4 indexes Y3, Y2, Y1, Y0. So the loop is going from 0 to 3. Now look at it, Y of 0 is U and V of 0 replicated 4 times. So this is kind of aggregating it. So we know that U is a 4 bit vector which is an input. So you have U3, U2, U1, U0 which is ANDed with, U3 is ANDed with V0, U2 is ANDed with V0 and so on. So all of the 4 bit is kind of masked with V0. Okay, for Y0. When it comes to Y1, the same U is kind of masked with repetition of V1s. Y2 is nothing but U and kind of Y3 is U and V3, all V3s and so on. Okay, so you get 4 Y0, Y1, Y2, Y3 which is nothing but U is masked by this bit. Okay, so I am going to show this pictorially. You have a 4 bit U vector U3, U2, U1, U0. The first operation is that you take there is a V which is going from V3, V2, V1, V0. So initially the U is masked with all V0, say V0, 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 that is what is done here, and you get Y0 which goes from 3, 2, 1, 0. Then next is V1, then it is masking and you get Y of 1, 3, 2, 1, 0. V2 then you get Y2 and you say V3 then you get Y3. So it is going like this, the arrow is going like this one by one, and here the arrow is going like that. So maybe I should have made it kind of opposite, but then I hope it is clear. V0 make Y0, V1 Y1, V2 Y2, V3 Y3. Okay, now maybe you get an idea what possibly could be the circuit, but let us wait, let us look at, go ahead, see the next part of the code. So this is a very simple code, but this is how the circuit is coming up. So I think keep this in mind. Let us go to the next part of the code. Okay, now here we form the Y's from U and V, that is a game, and in the second part we are going to make X from Y and temp, and you know that the temp is just zeros. Okay, so let us look at it. The X0 which is not in the loop, probably which could have been in the loop, but let us see. X of 0 is temp 3 down to 0 which is nothing but 4 zeros, and Y of 0 is this 4 bit. So you have 4 zeros then appended with y of 0. Okay. Now we get to the loop. Loop start with, because 0 is already made, loop is going from 1 to 3 and you say let us take the first index x of 1 because x of 0 is already there, x of 1 which is temp 3 down to I, that means 3 down to 1. Here it was 3 down to 0, 4 zeros, but here it is 3 zeros, then y1 now. So the earlier was y0 was appended, now we append the y1, it is appended with 3 zeros, y1 and temp I minus 1, that is 1 minus 1, temp 0 down to 0, that means 0 only, 1 bit, so you put a 0 here, that means 3 zeros, y1 and 1 0. Okay. Now you can guess when it comes to x2 this becomes 3 down to 2, then you have 2 zeros, y2 and it is 2 minus 1, 1 down to 0, 2 zeros. And the next loop when it is x3 it is 1 kind of 3 down to 3, 1 0 y and 3 zeros. And in addition you see as the loop goes, initially we have 4 0 and y. Now when it comes to x1 it is 3 0 y and 1 0 plus this is the previous one. So these two are added. When it comes to x2 whatever those two added is added with the new value and so on, and when you get x3, x3 is assigned as w which is the output. Okay. Now let us look at that picture. So we initially put okay, now come back to this, we had u, we had v, each of the first least significant bit of v0 is masked, you get y0, another bit is masked, then you get y1, next bit is masked with the u, y2, y3. Now you are forming all zeros, then put the y0, then you shifted version of y1 is added together, then you shifted version of y2 is added to it and shifted version of y3 is added to it and you get w. So it is you are getting the point, so you know that it is nothing but shift and add, so it is like it is multiplying, and if you look at this is nothing but forming the partial product. So you have a multiplicand which is 4 bit u3, u2, u1, u0, you have a multiplier which is 4 bit. So the first partial product is formed by the least significant bit of the multiplier, ANDed with this multiplicand you get the first partial product, then the V1 is ANDed with this, you get the second partial product, V2 is ANDed with this, then you get the third partial product, and then V3 is ANDed and you get the fourth partial product. Okay, that is what is done here. So you get 4 partial products, and now when it comes to this structure, it is nothing but partial products are shifted left one by one and it is added together. So it is like the partial products are added to get the product. Okay. So this, though I am showing this adder, there is this can be kind of it is showing 3 adders and parallelly it is added because it is a generate loop. It is not that the same adder is used each time a new adder is used because it is replicated. So you get a parallel adder. So it is a multiplier, but it is not a kind of iterative multiplier, it is a parallel multiplier, and the name of this multiplier is called array multiplier because you form an array of the partial product and you add it parallelly. So it is an array multiplier, it is a 4 bit unsigned array multiplier. Only thing is that normally when you refer to the textbook to avoid the rippling, something called, instead of a ripple adder, a carry save adders are used. Here you know that when you add this there is a rippling here, then there is a rippling here. It is possible to avoid the rippling kind of because the idea is that say you are adding these 2 bits, it does not matter whether the carry comes here or carry comes here. So it is possible to put the carry of this stage along with this here. Similarly carry of this stage can come here, the carry of this stage can come here. So that gives a kind of to reduce the ripple, otherwise it ripples and so you will get kind of 4 plus 4 8 rippling. It's possible to avoid the rippling using carry save adders, but this is a kind of, the idea is not to kind of design the array multiplier with the carry save adder. It is a practice in kind of working out from the code written, inferring the circuit which is implemented. And as I have shown, though the code looks a little crazy, it's very easily you can write and work out the underlying hardware. Okay. So only thing is that it has to be done systematically. You have to work on the pen and the paper. Okay, when I say pen and the paper, definitely you can write on your tablet or the note tool, or I don't know when this course is being recorded in November 2013, maybe somebody is watching in 2016 or 17, if at all it is done, then I don't know what is the technology, maybe whatever may be the technology, you can kind of you work it out. Okay, literally work it out on whatever tool you have, I would say on a paper pencil, then things will be very clear. There is no kind of ambiguity. I have taught you what the code means, and now it's a matter of patiently working systematically, then you will get what is the circuit. And in the process you can add, like suppose somebody has given a code like that, you can definitely infer that the ripple adder is being used, there is a lot of rippling, maybe we can replace this ripple adder with the carry save adder and make things faster, the critical path delay can be reduced and so on. So that's a advantage of kind of working the hardware from the VHDL code. So that should be kept in mind. So let us move ahead, one more example that has to be let us look at this example. So I want to design a synchronous 4-bit up down counter with the parallel load feature. Okay, that means it is a synchronous counter 4-bit. It should count up when the direction is 1, down when the direction is 0, and there is a load signal and 4-bit input. When the load is 1, it should load the counter with the input value, and depending on the direction, when the load goes low, depending on the direction it should go up or down. Okay, and we will first we will do is that we will write the block schematic, then we will write the behavioral code step systematically from this block schematic which is kind of drawn. So you know that the 4-bit counter needs a 4 flip flops, you have the clock and reset. Okay, so like when the reset comes the count is 0, and when the clock comes the game starts. The first thing is that you know that in a parallel load counter we need to have the priority for the load. So we will put a mux here, okay, to the D, and the select line is load, and when that is 1 we supply the input. Okay, if it is 0 then we have to put the count part. Okay, so let us put that so we put a 2 to 1 mux at the input because that is the highest priority, and we have seen that the highest priority will come near to the D. Okay, near to the D, because that is the one which gets effect first. So when the load is 1, this D in gets loaded into the D. If it is 0, now the direction comes. Now we have two things to do. If there is a direction is 1 then it up counts, direction is 0 it down counts. So what we do is that we put a 2 to 1 mux here, the select line is the direction. If direction is 1 then what we do, we have to increment this because it is Q. So you take this Q back, put up +1 to the 1 input of mux. Similarly if direction is 0 then Q has to be decremented. So Q is put through a -1 and put to the mux. Okay, so let us put that. So we have a 2 to 1 mux, there is a direction signal. If it is 1, Q is taken back to as input, then we have a +1 which goes to the mux, and if it is 0, Q is going through a -1, it goes to the 0 and it goes there. Okay. So now that is simple. We have 4 flip flops, reset, clock, which is common. We have the highest priority load, which goes to the first 2 to 1 mux, and load is 1, this goes there, load is 0 depending on the direction. Now direction is 1, then Q is Q plus 1, else Q is Q minus 1. Okay. And that's simple. Now actually like the design is over. Now if you look at this, you know that this entity has, say, reset as input single bit, clock as input single bit, load as input single bit, direction is input single bit, DIN is an input which is standard logic vector 3 down to 0 because 4 bit. Then we have a count which is output which is 3 down to 0 4 bit. That then this structure shows that count is also input to it, and we know that the VHDL doesn't allow. So we declare an internal signal called Q, and then we use Q as the to write the code, and in the architecture statement region we assign this Q to the count. Okay. Now if you look at the VHDL code, symbol, process, clock and reset. If reset is 1, Q gets other 0, else if clock even clock is equal to 1, under that if load is 1, Q gets DIN, else if direction is 1, Q gets Q plus 1, else Q gets Q minus 1, end if, sorry yes, end if, that's it. So that's the whole code. The moment you see this, the code is, there is no need to write the code, you know, it's a mechanical process. So it is possible to generate the code if you want, you know, somebody draw a block schematic, it is possible to generate the VHDL code out of the block schematic. Okay. It's for a computer science student it's very easy, you know, from this kind of structure to generate a VHDL code, it's very straightforward. Like you have a tool to draw, like the moment you put the draw, like you are only allowing the designer to draw, so you know what is happening, and you keep you know adding the template. You have a template code, then you can keep, you know, generating the VHDL code. It's very easy. So let us look at the kind of the code. You have the library, and we have standard logic 1164, then standard logic unsigned because we are going to use a plus. As I said, clock, reset, load, direction is 1 bit, DIN is 4 bit input, count is 4 bit output, then the Q is the same as count, which is signal 4 bit, count gets Q, then we start the begin. Okay, in the begin count gets Q, then you write process, clock, reset, begin. If reset is 1, Q gets other 0, else if clock even clock is equal to 1, then underneath all that is coming behind, and this has highest priority, next this has a priority. So if load is 1, then Q gets DIN, else if direction is 1, then Q gets Q plus 1, else Q gets Q minus 1, end if. Okay. So and this end if, and this is the memory end if, this is the combination circuit, if this represents the combination circuit with kind of priority, and this represents the memory end if because there is no else, and end process, end the architecture. So that is very simple, and that is how you should write the code. Very straightforward, there is nothing to worry. But if somebody say like you give this spec and you start like that straight away without any clue whatsoever about the circuit, and most people try to do that, you know, they kind of some vague idea and you know start assigning things, and things can go wrong because you will be wondering, you know, something goes wrong, then you will be playing with the if. You say okay, let us say instead of putting the if else here, you put something else, write another nested if and so on, because you have no clue on what is the circuit, and you will waste a lot of energy in going. But if you know as we have learned what is the meaning of this syntax as far as the circuit is concerned, then it's very easy, very easy to write. After a practice these kind of structure will be in your mind, you don't need to kind of expand it. You can just show us a block with the load direction and some way to indicate which has kind of priority over the other and things like that. Some kind of notation you can use, then straight away you can code it, it's very easy. So I think it's some kind of logical place to stop for a while, because we have taken quite a lot of VHDL, but that is to put you in a strong footing so that when we go to the tool, take a case study, try to implement, you are kind of thorough. So in this class we have looked at the carry lookup data the VHDL code, then we have seen basically the ripple adder, carry lookup adder, then some examples of some random circuit, how to code it. Then basically we have looked at the code of an array multiplier and worked out the underlying circuit, and without even bothering about what is the functionality. Of course you are writing an kind of exam and you have such a kind of question, then you are kind of finding like you have a shortage of time, then definitely you can guess and jump to conclusion. But when you are doing the serious design in a design team, you should not do that. You should do as I kind of as I have shown. But when you are with the serious design, you should not guess anything, you should work it out and info what is going on. And the last thing we have looked at is that given the spec of a counter, how to draw the block diagram and how to write the VHDL code as a one to one. What is shown in the block diagram is a code written. You give it to any synthesis tool, it is going to generate the same circuit. Maybe it is mapped to some inbuilt block as a single unit or multiple unit, it does not matter, but then we are not sure, maybe the multiplexer in there is implemented using some special resources within an FPGA. But that apart from that, apart from the technology, the block schematic which is generated by the synthesis tool will be exactly same as what you wanted, what you have drawn on the paper or what you have written the code, you are 100% sure about that. So that's a kind of thing I want you to do as a designer, and don't think that anything complex will have much more difficult than this, because ultimately we have seen that you have a complex circuit, then we are going to break it down hierarchically as data path, then controller, then we are going to data path itself is going to be broken down to this level of detail, and then you can write the code in a very straightforward way. You don't have to you don't have to be very happy that you get a C code to VHDL compiler. You can do that if you are in short of time, or a software engineer is trying to do the hardware design and so on. But I don't see any big point in doing that. Definitely the tools will improve as we go along the standard, but still it will be kind of template based. It cannot be kind of artificial intelligence and things like that, machine learning and things like that. But maybe it will come like that, but at least for the time being it is kind of there is underlying templates. You map you infer the structure architecture and try to map it to the standard structures and so on. So let us stop this the VHDL part here, and let us for at least 2 lectures let us get back to the digital design, so that we can continue maybe with the VHDL little more. We will go hand in hand. So let us move on. So let us come back to the digital system design part. Now very quickly I want you to run through the last thing we have done. Hopefully I am able to I am putting the thing correctly. So the last thing we have discussed in digital design was a case study. If you have not familiar if you have forgotten, or if you have not taken that part of the looked at that part of the lecture, go back and look at it, okay. So what we have done was we have an ADC. What we have tried, normally ADC is kind of interface to a host CPU or a microcontroller or a processor. What we are trying to do is that to kind of take the load off the processor by having a controller controlling the ADC and putting the data to a temporary storage, and when it's kind of full the host will read it. That was the idea, and we found that the best candidate for this is FIFO, because you write the data in order, you read the data in order. There is no, and it is a one way data flow. So you put the FIFO, so you put a controller gives the start of conversion, end of conversion comes to the controller. In addition, controller has a clock and reset, it gives the FIFO write, and when this becomes full it interrupts the host, and host will read it, and host give a start for controlling the whole operation. When it is start is 1, it keeps on doing it, and when it is 0 it stops, and this is the data path FIFO, and we are, at least in this case, we have assumed FIFO is there already, and we have looked at the controller, and first thing we have made some assumptions, that it is, and we have drawn a timing diagram. We wait for the start, when the start comes give a SOC, wait for an end of conversion, give a write signal. Then we said that this is can be a narrow pulse, in one state you can give an output, but this should be of some width and we need to generate that time properly. So we decided to put a counter as a subsystem which is controlled, the reset of which is controlled by the same controller or state machine, and when it is equal, it is decoded for a particular value, then gives a time. So the idea is that when the FIFO write is given, the reset is removed and it starts counting, and you wait for this time. When it reaches that pulse, get that pulse, then you put back the reset and terminate the FIFO. So we have updated the timing diagram, added this, when you put this low the reset is removed, wait for this, and from this we have worked out an algorithm like wait for the start, give start of conversion, wait of end of conversion, give FIFO write, remove the reset, wait for the signal and terminate everything, go back to the same thing, okay. And that was the control algorithm, and we have written a state diagram and the exactly similar thing. And so there are inputs, transition, states and the output, and we have decided to use D flip flop for state binary encoding, so 0001 1011, and from this state the input transition you can work out the next state table, state output you can work out the output table. So we have done that. You have this is the controller, we have basically the state variables or the flip flops which gives the present state, in our case 2 flip flop, and that along with the input decode the next state, and upon the clock next state is loaded, and in each state, the present state, the output is decoded from the present state as a function of the present state or as a function of input and the present state. If it is only the function of present state is Moore, if it is a function of present state and input then it is Millet, and we have written, as I said, from the input and the present state and the transition this table, then you get an equation for D1 and D0 in terms of the present state and the input, then you can minimize, implement it. Similarly for the output, you write the output in terms of the present state and you get output as a function of present state, you form the equation and minimize it, and that is a whole methodology, and basically up to the state diagram is what the designer has to put effort. Then the tools come into picture in all minimization, and ultimately to test and debug you use some kind of equipment, and the designer's involvement is there. Here designer gives some kind of inputs, and that is what we have done. We have seen the whole process of designing Of course the data path has to be designed. So let us now take some issues in the state machine itself, the controller. The first thing is that we know that we have happily put like when we discuss the state diagram, you see here okay, the state diagram is here. So we have shown upon the reset, that means at the beginning when the power on reset come, it should start with S0. Okay. It can be 0 0, it can be any state, it need not be 0 0, but it can be any state. But the game is that this reset has to be implemented, you should not forget that, that is very dangerous. You work out everything but you forget to implement reset in state machine, then you power on, it can come anywhere. Okay. It is very dangerous. Luckily we have only 4 states and 2 flip flops, but assume that we have say 6 states, then we need to use 3 flip flops and there are 8 states, there will be some unused state, and by you power it on without a reset, and if it goes to some unused state, we do not even know what is the behavior of the state machine, very dangerous. So it has to be properly reset. So that is what we are going to see that. So let us look at that. Okay, this is the state machine. We have the flip flops, present state, next state logic and output logic. So very simple. If you have reset, asynchronous reset in the flip flop, just connect the power on reset to that, and at the power on it will come to the starting state. Once it comes to the starting state, then you have the control, you are the one who is designing the state machine, and you can at the end of the iteration you can bring it back to the whatever state you require. You need not come back to the starting state depending on the application. It can go to some other state and wait for some input, but you have to at the beginning at the power on you have to bring it to a starting state, and that is where it is used. And this is like in VHDL coding, this is simple because this is combined with the flip flop. Okay. So you can treat this as a kind of process for a flip flop, then this reset is implemented along with that flip flop as the asynchronous reset of the flip flop. Suppose take the case where the flip flops in the technology, whatever the technology used, be it ASIC or an FPGA, assume that this reset is not available, then suppose there is no reset at all in the flip flop, then what we have to do is that we have to introduce a synchronous reset. As the name suggests, it is something to do with the D. So it is very simple, you add an input reset here, okay, and change the next state logic, and we have seen the truth table can be changed, or we are going to write the VHDL code. So in this somewhere we are going to say if reset is 1, then this next state is the starting state, then that is done. Okay. So if this is not available, then use a synchronous reset, but not both, so I have removed that, and if use synchronous reset, if not available, use asynchronous reset, if it is not available use a synchronous reset. So that is done, and from the experience what we have with the kind of data path design, a clever student can already infer what could be the circuit in terms of, we have shown for a counter with the load signal, this reset has the priority, like say there is input, there is present state, but definitely we know that synchronous reset has the priority. So if you look at it, it is equivalent to kind of putting a mux here, okay, and the reset is the select line, and when the reset is 1, a 0 goes there, otherwise this next state logic comes here. So like if you write a code for synchronous reset and give it to the synthesis tool, that is going to happen, at the output of previously written code, previously generated circuit, you are going to have a 2 to 1 mux where the select line is reset and you get a 0. Okay, that is what is happening. So I'm kind of reinforcing what we have learned. Probably I could have shown the picture, but it takes a lot of effort to draw these pictures and put it. I have already invested a lot of energy. So but I think you can kind of imagine what is basic idea here. So that is about the power on reset. And when it comes to the VHDL, we will go back to the VHDL coding of the state machine, though it is nothing kind of nothing great, because we know how to code flip flops or registers. We know how to code the combination circuit, because this is a combination circuit, this is a combination circuit. We have seen that you could combine the output logic with the next state logic, but after all it's combination circuit and we know how to code the combination circuit. So but yet we will see that because the controller is one important part, and we will see how to properly code it. And it is also there are different ways of coding it, but it is very specific to maybe the tool. There may be 6 different ways of coding it, but your tool may not understand everything, then there is a problem. So we will see that. We will go back to the coding of the VHDL. Let us look at the next topic. Okay. Now in this very conveniently we have shown a clock, okay, and that is what all the textbook do, kind of they show a clock, okay, and say the clock is there, but what should be this clock, okay. So what should be the frequency of the clock, that is the question, okay. Many a times it is not addressed, and you are kind of most of the time when you are in an academic you are answering some kind of most of the time some exam where it is enough that a line is drawn and you write the clock, okay. So you are saved by that, but in real life you have to give a clock, okay, and so we have to decide what should be the clock, okay. So definitely you must be getting some kind of idea saying that this probably can suffer or tolerate a range of frequencies, okay. Let us assume, let us try to find out what could be the maximum clock we can apply to this, okay, and what could be the minimum clock, okay. So let us look at the maximum clock and let us look at the minimum clock, okay. So the maximum clock, you must be already getting the idea, it has something to do with the delay of this logic, delay of the flip flop and delay of this logic, and we have already seen the maximum frequency of the state machine, which is nothing but the maximum frequency of a data path or a register to register path. This is a sequential circuit, but you have a data path as a pipeline, it is all same, you have some registers, some flip flop, its output is going through a combination logic and is going to some other flip flop. In this case if you have Q1 and Q0, Q1 output may go through some circuit, go to D1 or D0 and so on, okay. So there could be 4 paths, Q1 Q0 D1 D0, 2 by 2 you have 4 paths. So you know that if you consider that the clock comes, there is a TCQ delay, there is a delay through the combination circuit, and that data has to be here setup time before. So the clock period should be greater than TCQ max, T comp max plus T setup max, okay. And we have also, with the incomplete information we have, this given a clock, the output is kind of appear here after TCQ and T output logic. So whichever is greater, whichever this is greater or this is greater, we choose. Definitely if it goes through some other combination circuit to a register, we have to consider all that, and that is what when you really design, the tool is going to look at the whole path, this is just a picture, but ultimately when you design, this is going through a register, output logic, some combination logic, and ultimately it is going to a register, and the tool is going to analyze that, that you should keep in mind. So let us put the maximum frequency, okay. So we have a maximum clock frequency which depends on delay of the clocks, maximum clock frequency or the minimum clock period is T clock min should be greater than max of TCQ max plus TNSL max plus T setup max or TCQ max plus TOL max, and there could be kind of some more terms here, but kind of with the information we have, I am putting this, you can add that. But suppose you have designed a state machine and you find the maximum frequency is say 1 gigahertz, this this can tolerate, and is it a good idea to clock it at 1 gigahertz? Maybe the system which is controlling, which is the data path which is controlled by, say we have some data path which is which the state machine controls. Suppose that is working at say 100 megahertz. What is the point, that is dissipating so less power, but this is furiously clocking at 1 gigahertz, dissipating a lot of power because it is switching. So there is no advantage in working at the maximum frequency. We have to see how much minimum we can go, because in terms of the power dissipation that's the best thing to do. Like without after all the state machine alone cannot do anything, as long as it allows the data path to proceed at the desired throughput, desired frequency, then we should choose a frequency of the clock for the state machine such that the data path works properly at the desired, it should give the desired performance. Then we can minimize power in the state machine. So let us think, let us ask this question, what should be the minimum frequency? That is the great, that's a right question to ask. So maybe I think you should think what should the minimum frequency depend on. So that's a question to ask. The answer is, maybe I will put something, we are basically controlling a data path. So these inputs are coming from the data path some output, and these outputs are going to the data path input, and what we are trying to do is that we are trying to look at various input, step through various sequences and control that data path. So essentially it has got something to do with this input and something to do with the output, because that is where the game is. There is nothing extra, because there is a clock, there is a reset, everything else is coming from the data path. So it must got something to do with the input, something to do with probably something to do with the output. So let us ask this question. So what should be the minimum clock frequency? Now to illustrate I will kind of put some inputs and let us see that. So assume that we have 3 input to our state machine. That means we are looking at this, say these inputs are 3 inputs from the data path, it is some output of data path in 1, in 2, in 3. And to make our life easy, we are assuming they are all kind of square waves, which is not true. In real life you do not get anything like this. You may not even find a scenario where, a very rare scenario where everything is kind of square wave, but let us put this. So that is where, so I am trying to put a clock. The best thing is that when you try to analyze something, then you should put some simplest case, simple assumption. Suppose in maths you are trying to do something, say a kind of matrix multiplication with which is a 10 by 10, and you are trying to understand something. Maybe you are trying to understand something about eigenvalues and eigenvectors and so on. So it's very easy. Suppose you put a 5 by 5 matrix and trying to work out, you will not get any kind of intuitive idea. But the moment maybe you take a simple case of 2 by 2 matrix and a kind of 2 by 1 vector, and you try to infer these, draw a kind of graph, draw a picture, then you will get some intuitive idea. So every time when you try to kind of understand some fundamental, you put simple thing, you don't make very complicated. So that's why I put a very simple picture which is not real life. Then once you get the basic idea, then we can bring it to the next level of reality. We can bring back to the reality close to real life. So what I am showing is that I have shown 3 inputs, and you know that this in3 is a some frequency, maybe 100 megahertz, in2 is 50 megahertz, and in1 is 25 megahertz. Okay. So now I put a clock, okay, to see we have to see what is the minimum kind of frequency. So I just put a clock, okay. Of course I have worked it out, I have manipulated it for you to understand, but look at this, okay. And this is working on the positive clock edge, okay, like that, and you see that when this clock comes, say in1 is 0, the next clock one in1 has changed, no problem, it is detected within a clock period. Again it is still 1, no problem, it has gone to 0, that is detected. You take the in2, when the clock came, in2 was high, it is detected, then it went low, then this is detected and this change is detected. But you take a look at this in3 and you see that the clock edge comes and that is sample, and this is 1, and there is a transition to 0, it comes back to 1, but when the next clock comes it is still 1, it's still 1, it's still 1. That means there are some changes in one of the input, but since we have chosen a particular clock frequency, this is not detected at all. So this shows that this clock frequency is not going to work, maybe this is too low a clock period, okay. But suppose I put a clock like this, say now there is a positive clock edge, yes, it is detecting that it is 0, and when the next positive edge it is detecting that it is 1, next positive edge it is detecting that 0. So it shows that the clock frequency of the state machine has got something to do with the input changes, okay. So definitely we know that there is a change here. So if a clock has to come, the clock period has to come within this thing. So we can say as I to start with, I make a statement saying that the clock frequency should be twice that of the maximum clock frequency, okay. So we are coming to probably the end of the lecture, today's lecture. I will continue, I will complete this portion. So we looked at 2 parts, one is the reset, use async reset or sync reset, and the maximum clock frequency depends on the delay of the blocks. Minimum clock frequency has got something to do with the rate of change of the input to the state machine, which is output of the data path. So please go through whatever we have covered in this lecture, revise it, learn well, and I wish you all the best and thank you.